students, welcome to the practical sessions of measurement and instrumentation. As a part of the first experiment in this subject, today we are going to learn about study of LVDT. In the part of theory, we have seen that LVDT means linear variable differential transformer. Now, this LVDT is nothing but a transducer which is going to convert a displacement into an electrical signal. So, let us study how this linear variable differential transformer is going to convert any displacement into an electrical signal in terms of electrical EMF. Okay, so let us get introduced to what devices we are going to use for the purpose of this experiment. Now, as you see here, this is what we call as digital panel meter for the LVDT kit, and this is the actual LVDT kit. Okay, so let us first learn about how this LVDT is designed and the arrangement is been done. As we have seen in the part of theory, what we are going to do is we are going to have a hollow cylindrical former in which in the hollow portion we are going to have a core which is free to move. Okay, so whatever cylindrical portion that you are able to see here, as such, this is a hollow cylindrical portion over here. Okay, and this is a rod which is made up of any magnetic material which is free to move in and out. So as such, okay. Now here if you see, whatever total cylindrical portion is there, the total cylindrical portion is divided into three parts, out of which if you see at the center you will find a small notch over here, as such, here and here. Okay, between these 2 points if you see, there is one winding to which we are going to call as a primary winding. Okay, now we are going to give a constant source of AC supply to this primary winding which is at the center part of this particular cylindrical portion. To the left hand side of that cylindrical portion and to the right hand side of this cylindrical portion, again we are going to find 2 windings from here up to this particular notch. This is one of the winding, what we call as secondary winding number 1, and similarly from here to here, from this notch up to the end of this cylindrical portion, there is one more cylindrical winding, secondary winding, what we call as a secondary winding number 2. So as such, the total cylindrical portion is divided into 3 parts. At the center part we have wound a primary winding to which we are going to give a constant AC supply of a constant voltage, and to the either side of the primary winding there are 2 secondary windings, secondary winding number 1 and secondary winding number 2. Now, as we have seen in the part of theory, what we are going to do is, as and when the supply is given to the primary winding, what happens is the flux is going to get produced in this primary winding. Now, as since inside this, whatever magnetic material core we are going to use, that core is available at the left hand side as well as right hand side of this particular primary winding. Now, if suppose initially, if this rod is, or a core what you can say, is kept at a center position, okay, that is what we call as a null position, then what happens is the part of the core towards left hand side of the primary and the part of the core towards right hands of the primary winding will be same, and due to that what happens is whatever flux that is produced in the primary winding will equally link with the secondary winding number 1 as well as secondary winding number 2. Now here what we have done is, in case of the 2 secondary windings, these 2 secondary windings are connected to each other in series opposition fashion. Due to that what happens is the total output what we get as a secondary winding will be equal to the EMF induced in secondary winding number 1 minus the EMF induced in secondary winding number 2. That is, output voltage of the secondary winding will be equal to ES1 minus ES2. Now when the core is at exact center position, what we call as zero position or null position, at that time part of the core towards left hand side, that is secondary winding number 1, and part of core towards the right hand side, that is secondary winding number 2, is same, and hence the flux linkages at the two secondary windings is same, that is ES1 and ES2 both are same. So when ES1 and ES2 both are same, the net output what we call is ES1 minus ES2 will be absolutely 0. Okay, so that is the EMF of the secondary winding, and that EMF of the secondary winding that we are going to read with the help of digital panometer, and you will be able to get the value of that voltage over here. Now whatever voltage that we get over here, that is actually calibrated in terms of millimeter. So as written here, digital meter that is going to give display in a millimeters. Okay, so directly it has been calibrated in such a manner that EMF induced will be proportional to the mmf of millimeter of the displacement. Okay, so let us now start with the experiment. Now what we have is, this is a digital panometer as said. So here from the socket, single phase 230 volts AC supply is provided to the digital panometer. Inside this we have used a step down transformer which is going to decrease the 230 volts AC into 5 volts AC. That 5 volts AC is available at the 2 points where it has been said as primary winding. Okay, now from here with the help of red wire and black wire, we have given a 5 volts AC supply to the central portion over here, that is primary winding, to the LVDT kit. Now after the series opposition connection, whatever secondary winding output we are going to get, that secondary winding output through the cables with a yellow wire and blue wire, that has been given back to these two terminals where we are going to get the variable secondary voltage, and this variable secondary voltage is then fed inside this to the A to D converter, and that will convert it into digital form, and that EMF in the digital form will be displayed in this particular panel, which is nothing but a millimeters of displacement. Okay, now let us study how this meter is going to work. Initially what we are going to do is, we are going to connect the primary and the secondary winding of the kits to this digital panometer along with the color codings. So as we have seen, the red and black wire is for primary winding. So here red wire and black wire are connected to red and black terminals of the digital panometer where there is a primary winding supply, and the secondary winding is connected across yellow wire and blue wire. So yellow and blue wire are the two wires that are connected to two yellow and blue terminals where the secondary winding output we are going to give feed to the LVDT DPM, digital panometer. Okay, now so as to get the actual displacement, we have been given here the scale, linear scale. Okay, so this is the rod which is free to move inside this particular hollow portion. So initially this rod we are going to keep at the 0 position, means what, here what we call as a 0 position, 0 millimeters is the displacement what we call as a null displacement. Okay, so on the scale we have placed it 0. Now we are going to calibrate the actual scale with the digital panometer scale for 2 times. Initially we will calibrate it for 0 and then for any arbitrary value. Now here if the displacement is in this side, we are going to get what we call as a positive displacement. All the values what you get is positive. And similarly, instead of this, if you move this rod towards left hand side, whatever displacements we are going to get are what we call as a negative displacements. Okay, so initially let us keep this rod at the 0 position, what we call as a null position, and at that null position we will check what is the DPM reading. So let us start the mains of the digital panometer. Now as you see here, right now for 0 position it is showing certainly a random values. Okay, so here we will again adjust it to 0 exactly. So from front if you see, we have adjusted to 0 on the scale, and here if you see right now it is showing certainly a 0. It will fluctuate for a while, but we have to keep in such a way. Now it is becoming 0. Okay. Okay. So with a small error of 0.02, 0.03, it's okay. So as you see here, again, this is actual scale, actual DPM position, actual rod core position is at 0 and the DPM reading is slightly 0.04. Now this is what we call as a null position calibration. And now similar calibration we are going to again do to some arbitrary value. Okay. So let us move this core towards the positive side. So what I have done is I have moved the core, I have made the displacement of the core such that now the core is at 15 mm. Okay, so as you see here, when I am making it at 15 mm, the DPM what we are going to get reading is 15.02. So there's no need of adjustment again. So when the core position is actually 0, the DPM was showing us 0. Now the core position I have kept at 15 and the DPM value is also 15. Now our calibration is ready. Now what we are going to do is we are simply going to give a displacement to this core, okay, either in positive side or in negative side, and accordingly whatever values that are being shown in the form of EMF in the DPM, the same is calibrated as millimeters, and that we are going to note down. Okay, so let us start with, let us suppose I make a displacement of the core physically to 19. Okay, so let us see here, a slightly less than 20 I am positioning. Okay, okay, so one less than 20, that is 19 mm is the positive displacement here, and what you find on the DPM is it is 18.92. So what we are going to take the readings as actual displacement in millimeters on the scale and the value that is being read by the digital panel meter. Okay, that's how we are going to take the readings. Now let us make a positive displacement of 10 millimeters on the actual scale. So as you see here, right now I have kept the core position at 10 millimeters and the DPM is showing us 10.10. Okay, so let us take this as a reading number 2. So actual scale position is 10 and the DPM is showing us 10 mm. That means the displacement is getting converted into an electrical signal. Okay, now let us put this position at 5. With a fair approximation, if you see, this is at 5 positive displacement and the DPM is showing us 5.08. So let us take this as third reading. Now I will move this core towards the negative displacement. Okay, so as I move this, let us take it as -4 suppose. Okay, so what I have done is slightly less than 5 mm I have taken it as -4, and for the -4 value the DPM reading what I get is 3.9. Okay, so similarly now let us take -11 suppose. Okay, here if you see, slightly 1 millimeter more than 10 mm I have taken, and that is negative displacement. So -11 I have taken on the scale and the reading shown us is -10.87. And similarly let us take -15 now on the actual scale. Okay, here what I have taken is -15, that is negative displacement, and the reading shown is 14.92. Okay, and that's how you can take any 5 readings randomly. Okay, so that means a LVDT is a transducer which is going to convert a displacement into an electrical signal, and whatever electrical signal EMF we are going to get, that we are going to calibrate directly in terms of millimeters of the displacement. Okay, so that's all about this particular experiment, study of linear variable differential transformer as a transducer. Okay, thank you very much.